Hello everyone, my name is Kunal and I'm your physics tutor and we are actually doing oscillations and today is our lecture number 5. So let me give you a topic's name in which we are actually dealing with simple harmonic motions. So let me recap the things कि हमने क्या क्या चीजें cover करी हैं. So हमने actually in first lecture we actually deal with some omega time period frequency and all. Then हमने cover करी phase and phasor diagram जो हमने previous class में cover करे थे और we reached and we actually start calculating time period. यहाँ पे हमने एक conclusion पे पहुंचे थे और वो conclusion ये था कि wherever there is a single spring block system, our time period is equal to 2 pi root under m by k जो हमने कल कंक्लूड करा था कि अगर कहीं भी अगर आप मेरे पास अगर सिंगल स्प्रिंग ब्लॉक सिस्टम मिलता है तो वहां पे जो टाइम पीरियड होगी उस सिस्टम की जो टाइम पीरियड होगी वो क्या होगी 2 पाई रूट अंडर m by k. ये हमने कल कंक्लूड करा था. So now in today's class, we are actually move on to the same topic because in this chapter, our main goal is to calculate the frequency and the time period of the different kinds of system. So first system we are actually dealing with in yesterday lecture was single spring block system. Now in today's class, we are actually trying to calculate the time period of the such system in which series and parallel combination of spring. So let me give the heading of the today's topic. We are actually dealing with series and parallel combination of spring. Okay, so this is our actually topic. So first we will start with the series combination. So let me you can take any number of spring, but what I'm trying to do here is I am just taking two spring in series, and what I'm gonna do here is I am actually derive for nth one. So this is for first for series combination. So what is actually series combination? So let me draw it here. There will be actually two spring connected end by end. There is a mass. So it has spring constant K1 and this spring has spring constant K2. Let us assume that, right? And it's actually smooth surface. So I hope you'll all understand what is actually series combination. Two spring or two or more spring is connected end by end. So this is actually in such a manner. So it will be called as series combination. And each spring has different stiffness constant, may be same, but right now I am taking the in general case in which the both spring has different stiffness constant. So what I'm taking K1 and K2 as different stiffness constant, and I'm just derive it for two. You can take for NS. So what's my approach is I just derive for two and reduce it to an spring combination and spring series combination. So let me tell you there is a displacement of X and there's a force acting F. So what I'm trying to get here is in both spring, if the net, let me write it here. The net displacement by two spring is something X. So let me assume this spring is actually displaced by X2 and the first spring is actually displaced by X1. And what we know, the X1 plus X2 is actually our net displacement in the mass M, which is actually is equal to X. So this is our equation number one that we actually known, right? So what I'm assuming is there is a displacement in the first spring by X1 and there is a displacement in spring 2 by X2 and the net displacement by the two spring will be termed as X. And Now, if I talk about the dynamic, so look at here in this spring and for this mass. So there will be like K2x2 is equal to F. I'm just checking this dynamic. There is a force acting F, and this is actually is equal to K2x2. And this is same actually is equal to K1x1. If we are taking about this point, or we are just saying about this point, let us say P, and there is acting force F. So in this point, K1x1 is equal to K2x2, because in this spring force is actually is equal to the force occur in this spring. If I take about the dynamics, so it will be like this. K1x1 is equal to K2x2, and in similar order there is acting a force F. This is for point P. This is I'm termed as point Q, K2x2. So overall we can write this equation. Now, what can we do here? We can write a force is equal to something K equivalent into X, because finally we have to need in such manner. क्योंकि कल की जो मैंने 5 रूल्स लिखवाई थी उसमें हमने यही कहा था, पहले हमें सारी डिस्प्लेस इन इस पहले हमें मीन पोजीशन पहचाननी होती है, देन हमें डिस्प्लेस पोजीशन पे डायनेमिक्स लिखना होता है, मीन पोजीशन पे डायनेमिक्स लिखनी होती है. Then we are actually our main target is to reduce the restoring force in term of F is equal to Fr is equal to minus of Kx using the uh, mean value equations, right? So the same thing what I'm going to do here is finally we have to need the restoring force in such manner, right? And we have actually two things. The net displacement is X and all. So what I'm going to do here is we can write X is equal to here Fr by K equivalent, which is actually is equal to F by K equivalent. Now from equations 1 and 2, we can write here, let me write it here, F by K equivalent is equal to what we can write as X1. So we can write X1 as F by K1, right? And X2 as F by K2. So let me write it here. What we get? F by K1 plus F by K2. So what we get? 1 by K equivalent is equal to 1 by K1 plus 1 by K2. So this is actually for two uh, two spring series combination. What if for N or uh, M spring series combinations? So what I have to do here? Let me tell you. So 1 by K equivalent is actually is equal to 1 by K1 plus 1 by K2 dot 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 up to 1 by Km. So this is the in general case, and this is what two uh, two spring series combination. I hope it will be clear to all of you. Now, this is for actually series combinations. So actually we are gonna deal with the same thing. We can write like if there is two spring is given for K1 and K2 and there is mass M. Okay, so this is our smooth surface. So what we can do, we can write this whole system is equivalent to, we can write it this into single spring block system with K equivalent, which is actually is equal to if I solve this equation, so what you get, the K equivalent value will be K1 K2 by K1 plus K2, right? So it will be as easy as you think. So it will be like K1 K2 by K1 plus K2. And if I now talk about the time period, so all know that 2 pi root under M by K. So here K is actually K equivalent. So here the time period is, let me draw it here, smooth surface. So here the time period m by here the देखो यहाँ पे दो स्प्रिंग को हमने सिंगल we actually this is actually two spring one block system और हमने क्या करा हमने इसको कन्वर्ट करा सेम सिस्टम को one spring block system and we all know that for one spring block system the time period is nothing but 2 pi root under m by k. But here the k is actually k equivalent and its value is actually is equal to for two springs k1 k2 by k1 plus k2. So here we can write k1 k2 and divided by k1 plus k2. So this is actually for two spring one block system. Our time period is something look like this. Right. I hope it is actually clear to all of you. And this is actually the series combination. Right. Now let's talk in and there is some actually noted point. So let me write it here for series combinations. So the first is it is actually a displacement or divider arrangement. Why I'm saying so? Because the both spring has different displacement x1 and x2 as I mentioned earlier, right? Yeah, as I mentioned earlier, the both spring one and spring two has a different displacement. One has x1 and other has x2 because they have actually different stiffness constant. So that's why their displacement is also different. So that's why I'm saying displacement divider arrangement. But one thing that you have to notice, it is a common force arrangement too. Common force arrangement, right? If you notice there, the force is actually common, which is actually equal to F. K1 x1 is equal to K2 x2 is equal to F. So this is the thing that we have to keep in mind. In series combination, this is actually the displacement divider arrangement, and it is a common force arrangement. So I hope we'll talk enough about series combinations. So wherever you need to find somewhere we will actually deal with question as well. So बस आपको ये ध्यान रखनी है कि अगर आपके पास m स्प्रिंग दिया हो और जो कि सीरीज में कनेक्टेड हो विच इज एक्चुअली मैंने यही कहा एंड टू एंड कनेक्टेड हो एंड सो क्या होगा कि उसकी जो आपको उसको सिंगल स्प्रिंग में कन्वर्ट करनी है like m spring single block system दी हुई है. So what you have to do, you have to convert those system into single spring block system, and then you know that the time period for the single spring block system will be equal to 2 pi root under m by k. So you have to here the k is actually k equivalent, and you all know that how to calculate the k equivalent for the m spring series combinations, right? So this is actually formula we'll actually use to solve those kind of things. So now let's move on to the second combinations of spring, which is actually parallel one. So let me start it here. Now our actually second combination, which is actually termed as parallel combinations. Okay. So let me again derive it for 2, and we are actually reduce it to m or n parallel spring combinations. Okay, so this spring has K1 stiffness constant, this spring has K2 stiffness constant. And there is a force which is acting F on the system. So, okay, and it has mass small m, right? And okay, now what I'm trying to say here is we have to calculate its like there is two spring which is actually parallelly connected to a actually one block, right? This and this spring one and spring two is actually parallel connected to the mass, right? These both spring are parallel. Now, what I'm trying to tell you is if I displace that mass by x, so the both spring is actually displaced by x, right? So what I'm trying to do here is our force is there, and we have actually two force in this direction, which is actually equal to K1 plus K2 into X. Because both spring had some spring, let me try to do it here. Like there is both F. So both spring has a displacement X because both spring are parallelly connected. So both moves in a similar direction. Because look at here. If you want to say that, let me draw it here in rough side. If you want to say that if both spring has different uh, displacement, look at this has x1 and it has x2. And I'm assuming like x2 is greater than x1. So how is our block moves? Like in this, right? But what I'm trying to say, if like if you are assuming that both have different displacement, so our actually block is move in a tilted direction, right? It's not moving in a vertical direction. It moving something like this, right? If x2 is continuously greater than x1. So what I'm trying to say about you is if this block is moving vertical, so it has to be moved. So both spring has to be moved with same displacement, right? If the block has to move vertical, that's provided in the conditions. So it has to be moved the same displacement by the both spring. Okay. So this is the thing that what I'm trying to tell you. If both spring has different displacement, our block has actually moving in with a tilted direction, like in this way. But if the block has to move in a vertically, so what we have to do, we have to assume that both spring has same displacement. So like there is a force like K1x and there is a force like K2x. So if you balance it, so it will be equal to K1 plus K2, right? So what we can write it here, we can, okay, so we can write it here as force is actually is equal to K1x plus K2x. So force is actually equal to K1 plus K2x. So actually, finally, we need the force in this type, right? And we actually get. So here, actually, our K equivalent is nothing but K1 plus K2. F is equal to basically K equivalent is equal to K1 plus K2, right? So in general, let me write it here. In general, for M spring, M parallel spring combinations, our K equivalent is actually is equal to K1 plus K2 plus K3 dot Km. So this is the thing that you have to keep in mind, right? Now, uh, what I'm trying to tell you is what we done it here. Let me write it here. We have actually two spring. One has K1 and other has K2. And sorry for my diagram, but assuming that the both block have the both spring has parallel. So what I'm the same system, like there is a two spring one block system. So what I done here is I just convert this system as single spring block system, and it has K equivalent. So we all know that, and here the K equivalent here is K1 plus K2. And for if there is an spring, so you have like K1 plus K2 plus Kr. And we all know that the time period for the single spring block system is actually 2 pi root under M by K, but here K is actually K equivalent. So here is our time period is nothing but M by K1 plus K2. Okay, so this is the thing that we have to keep in mind. Okay, so there is some noted point that I have to wrote. Same as spring, actually same as series combinator. So there is actually displacement divider arrangement and common force arrangement. But here I actually uh, common displacement arrangement. As you look at here, uh, basically why I'm saying it has common displacement arrangement, because the both of the spring move to the same actually distance, which is actually termed as x. So it is actually common displacement arrangement, right? The both of the spring is has same displacement, which is actually x. And the second is force divider arrangement. Force divider arrangement. Okay. So why I am saying so? So look at here. Our force is actually distributed between two springs, K1x and K2x. So the this arrangement, parallel combination arrangement, is actually force divider arrangement and common displacement arrangement. And our series is actually common force arrangement and displacement divider, right? So these things that you have to keep in mind. And now combination of spring is opposite to actually combination of resistor. So there is actually we can conclude here combinations of spring is opposite to combinations of resistors. आपने एक्चुअली पढ़ा होगा कि 9th और 8th में कि लाइक अगर दो रजिस्टर let us say as R1 R2 is connected in series, so the R equivalent is actually R1 plus R2. But when two spring is connected in series with the stiffness constant K1 K2, the K equivalent is actually equal to K1 K2 by K1 plus K2, or we can write 1 by K1 plus K2. And when two resistors is actually connected in parallel, so our R equivalent is actually equal to R1 R2 by R1 plus R2. जो आपने पढ़ा होगा obviously, but when two spring is connected in parallel, the stiffness constant K1 K2, so here the K equivalent is actually equal to K1 plus K2. So actually the series combination of resistor is actually analog of we can term as like parallel combination of spring, and parallel combination of resistor is analog of like series combinations of a spring. So somehow we can connect it to the resistor as well, right? So this is the thing that uh, we are dealing with. So now it's time to deal with some problem, so we can understand how much we actually understand in this topic. So let me take some question, 2 or 3 questions, and you have to just find the time period. So question 1, find the time period. Okay, so there's two spring. देखो आपको कोई force वगैरह लिखने की जरूरत नहीं है. You have to just directly solve the question. There is a K and there is a stiffness constant 50. You have to find its time period. So what you have to do, let me solve it here. So my suggestion is to pause the video and try to solve it by your, because already we solved in just before, so you can solve this. And so we can write this to a spring one block system into one spring block system, and it has something look like this. This is K equivalent. And what is K equivalent is equal to? It is actually equal to K1 K2 by K1 plus K2 for 2. And K1 we can take K into 2K by 3K. So we can write it as 2k by 3. So this is actually our k equivalent. And we all know that the time period for this single spring block system is m by k, but here k is actually k equivalent. So 2 pi root under m by the k equivalent value is 2k by 3. So 3m by 2. So this is our actually time period. I hope it will be clear to all. Okay, कुछ भी डायनेमिक्स करने की जरूरत नहीं है. Just you have to find the k equivalent and it will be easy to just put in the formula which we already have. Time period equal to 2 pi root under m by 2. Okay, so now let's move on to the second problem. Find the time period. So this is k. This is 2k, and there's actually plate act. Okay, and then there is a and it has stiffness constant 6k. So you have to find time. So again, my suggestion is you to, this is actually easy question. You already deal with register combination, so you can easily solve this problem, right? Just you have to convert this whole system into single spring block system with finding actually k equivalent, and then you have to just apply the 2 pi root under m by k equivalent formula for time period. So okay, so just solve it. Otherwise, I'm going to solve it too. So what we have to do it here, look at here, this spring, if I'm termed as spring 1 and this spring I'm termed as spring 2 and this spring I'm termed as spring 3. So 1 and 2 is actually in parallel, right? This spring and this spring is actually connected in parallel. We don't know this spring 1 and 3, how it is connected. We didn't have any idea. But we actually have idea that 1 and 2 is actually connected in parallel. So let me reduce it to such system. And in parallel, our let me termed as k equivalent dash, which is actually equal to k1 plus k2. So it will termed as k plus 2k. It is actually equal to 3k. This we can write this both parallel and spring into one spring, right? By using k equivalent thing. Now its combination is actually 1 and 2 is combination is, let me call it as spring 4. We write in 2 spring we actually reduce it to 1 spring system, and this is actually spring 3. Now the spring 3rd and 4th is actually connected in series. So we can write this as single spring block system. And here the k equivalent is actually is equal to k equivalent dash into let me call it as k3 by k equivalent dash plus k3. And what is k equivalent dash value? It will be like 3k into 6k divided by 9k. So it will be 2k. So overall the k equivalent value will be 2k. And this is actually the single spring block system. So we all know that the time period is actually equal to 2 pi root under m by k. But here k is actually k equivalent. So it will be like 2 pi root under m by. Okay. So this is actually the final answer of this system, 2 pi root under m by, right? Now let's take the another example, the third one. So this is actually same as आपको बस यही किसी को ऐसे ही सिस्टम को चेंज करते जानी है, and then you have to finally convert, चाहे किसी तरीके का अरेंजमेंट दिया हो, your main goal is to convert those arrangement into single spring block system, because उसकी टाइम पीरियड के फॉर्मूला में पता है 2 pi root under m by k. So just we have to do so. Like let me take the question number 3rd. This time our block is in, there is a 2 strain, right? And it has given it has K2. And you have to find its time. Find the time period of system. Obviously, the both of this thing is actually connected in parallel arrangement, right? The both of the spring is actually connected in parallel arrangement, right? With the spring constant K1 and K2. And so we can write this whole system as, this is actually easy problem. K equivalent, where K equivalent is actually equal to K1 plus K2. And when we write so it will be K1 plus K2. And then what we can do, okay, the time period is actually 2 pi root under m by K1 plus K2, right? We have nothing to do. Okay, so my suggestion is to take some more problem, practice more. So it is actually easy. You have nothing to worry more about in this. So this is the actually whole spring block system, two spring uh, system, which is actually connected in series, parallel and all. Or okay, so now I'm gonna take here basically I am introducing here things which is actually termed as young modulus of elasticity. So what is actually young modulus of elasticity? So it is actually defined as uh, phi is equal to stress by strain. Okay, so let me tell you, like this is our, let me take here as a rod first. Okay, so this is actually our rod of length L naught. And if you hang a mass M on this, so there is actually, uh, let me tell you, this is actually original length. And when we, so there is actually change in its length. Like what I'm trying to say, take a rod. Actually, rod की जगह पे मैं क्या कर सकता हूँ? Take a uh, small, take a thin copper wire. Okay, and what you have to do, you have to just pulled it from both side. ठीक है, आपको उसको दोनों साइड से पकड़ के उसको खींचनी है. सो क्या होगी कि उसकी लेंथ में थोड़ी सी चेंज आती है. द सेम थिंग व्हाट आई एम टॉकिंग अबाउट हियर. आई एम जस्ट टेकिंग इट अ thin rod which has it has original length L naught, and I just hang a mass M on it. So I'm assuming that there's a change in its length which is termed as delta. So actually stress is actually defined as like pressure kind of thing. So it's like a restoring force by cross sectional area. Exactly, cross sectional area is A. I'm assuming that. And actually strain is defined as change in length by original length. Okay, so this is the thing that we actually derive here. Stress by strain. This is actually termed as Young modulus of elasticity. Uh, and it is actually material constant, obviously. So our stress is nothing but like a restoring force by cross-sectional area. And strain is actually termed as change in length by original length. Okay. So if I define here the Young modulus of elasticity, so our stress is a force, restoring force by area, and our strain is a change in length by original length. So this is our Young modulus of elasticity formula, and it is also termed as material constant. Okay, so the same thing we actually connect it with uh, in terms of spring. So there is a topic named as cutting of spring, which we will discuss in tomorrow's lecture. जिसका मैंने एज अ बेस फ्रंट बताया आपको कि young modulus of elasticity. So we are actually connect this rod to actually spring. So in tomorrow's lecture, we are going to deal with our new topic, which is actually cutting of spring. आज हमने क्या करा? If you notice one thing, आज हमने क्या करी कि दो स्प्रिंग को जोड़ा, and we add two spring either by series combinations or by parallel combinations, right? So now in tomorrow's lecture, what I'm going to do, I'm just cut that spring into two or more sections, and then I'm trying to find its a time period and all, right? So the things that you have to understand in today's lecture, we actually add two spring either by series combinations or by parallel combinations. So we and in tomorrow's lecture, we are going to deal with the cutting of the spring. हमें क्या करनी है कि स्प्रिंग को कट कर देना है फॉर some length पे जाके, and then we have to try to find its स्प्रिंग कांस्टेंट क्या होगी, स्टिफनेस कांस्टेंट क्या सेम रहेगा या चेंज करेगी, that these thing that we have to notice and find it out. So okay, that's all for today's. Thank you.